Today we're talking about Chapter 9, Web and Database Attacks. So our main objective, we're going to talk about how to perform system hacking and web and database attacks. And our key concepts are going to be web server vulns, tools and exploits, as well as the application vulnerabilities, tools and exploits. So we're going to look at both sides, the hardware that hosts the material, as well as the application itself, and then database attacks and attack tools. Now, there are several classes of individuals that are involved with a web server or concerned with it. And these have to be something that we consider when we're talking about either crafting or defending against web server attacks. The server administrator is first up because they're concerned with the server's security. It can act as an entry point into your network for malicious code, viruses, worms, trojans, that sort of thing. Now, this has become an even bigger challenge because web servers have become more and more complex over time, and there's a lot more features that are involved. And every feature, especially that deals with connectivity or ease of use, can possibly compromise aspects of our security posture. There are also unknown or undocumented options that can be incorporated as part of the development process for a web server that can lead to unexpected negatives. There can be detriments that occur. The network administrator is concerned with the fallout from problems that the server administrator may introduce or overlook. So, as in all things network related, you have individuals that involve themselves with this particular device, and there may be outcomes that are deleterious. Security problems that are introduced in this way or overlooked can lead to holes that can be exploited that would allow access to company resources and services. It can possibly be used to piggyback onto other connected servers that are like vendors or things like that. These administrators have to be aware that a web server needs to be usable by the public and the masses at the same time. A huge amount of external traffic as well as internal traffic. So that means that we have to make sure it's accessible yet secure. Definitely conflicting goals. Then the third in this listing here is the end user. Of course, we understand the public, right? The individual who will work most with the server, they're concerned with access. They don't really think about the mechanics of how it works or maintenance. They want access to content and services. You're not sitting there thinking about the back end of the Netflix infrastructure when you're trying to watch Stranger Things, right? You really want to just be able to press the button and the video that you want to watch loads up. Think about the software stack that builds in Java or ActiveX or PHP or any of the different databases that are incorporated. And these allow for some very real security threats. Now, what makes this even more impactful is that web browsers can also allow threats to bypass your company's firewall or your personal firewall and have a free ride into the internal network. So those things are considered to be very, very hazardous indeed. Then we also have to talk about the categories of risk. What's going on here? What is the possible threat? Server defects and misconfigs. We can have information that can be manipulated, intercepted, or stolen. And when I say manipulation, that can go up to and including just utter destruction. We can also have scripts that get incorporated or executed locally or remotely. Or we can have a denial of service attack that occurs. Browser and network-based risks. This can include scenarios where an attacker grabs network traffic. Very, very simple, being able to capture data in a stream between the browser and the server. And then browser and client-side risks specifically would be things that affect the user's system, such as crashing the browser or, again, information theft. You can see that happens at several levels. And then infecting the client system with potential malware. Web servers have the same vulnerabilities as any other server that provides external services. And then, not only for things that are being hosted internally, but being hosted externally, public-facing servers as well. Improper or poor web design. This is where attackers can observe tags placed in a web page by viewing the source code. I believe it's F12 that you can press in most web browsers now that will put you in inspector view. I know Chrome does it and Firefox does it. And you can see the actual HTML code that's being interpreted by your browser to produce the page that you're looking at. So there are some sensitive items that, if not obscured or if not properly stacked, if you will, the nesting process of working through something like PHP or certain types of advanced CSS, it can be very visible what things are. Certain variables might be named, potentially dangerous exposures, things like that. Things that could tell you the structure of the server, possibly allow you to do some directory traversal. So here are some examples of source code that might be a little bit sensitive. So if we look at the example in the top left here, form method post. So we're going to go ahead and post some kind of upload sheet. This is using a form mail structure. And if we look, we've got a couple of different input fields. We can see that we've got recipient, subject, required, etc. So there's a lot of information coming in from this particular site. Okay, now let's look down towards the bottom there. We've got some email addresses, hidden name, CC and BCC. If we look at the payments.someplace.com, we can make some assessments about what might be present in terms of subdomains or directly accessible items. This could allow us to target an attack very easily. If we look on the right and we look at form action, this is where we are posting information to some kind of order process, as opposed to just the mail form, being able to send a crafted mail template. So this is where we can see hidden fields that are being listed with a particular value. We can also see the product ID. So if those things can be tracked and manipulated, we might be able to actually trigger a discount, if you will. So here in the example, they say, this is a $6,000 item. If we go in and we change the price of the item from $6,000 to $60,000, or it might not even be that you change the value specifically. You might be able to have a discount scaler. If there's a coupon code that's applied or something else, and there is a passed-in variable that allows you to apply a particular discount percentage-wise across an entire order or something similar. You may be able to use buffer overflow or something similar to be able to drop it down by 90% or something crazy, which is very much what you're seeing here. You're going from $6,000 to $60. We're cropping off 100-fold of what this thing is. So again, at that point, if we don't have any kind of system check to make sure that things aren't being wonky, you could lose a significant amount of profit on a particular item just from the form being improperly structured. So we've got a nice little table of contents here to talk about all the different vulnerabilities that we can experience. Let me clarify, not all of them, but a significant number of the common ones. So we've got buffer overflow, denial of service, distributed denial of service. There's also distributed reflected denial of service as well. So you may see DDoS as well, DRDOS. Banner information, banner grabs we've talked about before. Permissions, error messages, unnecessary features, which we mentioned a couple slides ago, user accounts, and then SQL injections. Now, I believe this is the first time we've really talked about SQL, structured query language, and you'll see that when we work with relational databases, which is going to be a common feature of the web server, there's a lot of potential for vulnerability because of the nature of how those queries have to be processed. So buffer overflow occurs when an application, process, or program attempts to put more data into a buffer than it was designed to hold. So a buffer is just temporary storage to help kind of preload information to make sure there's a smooth transition as the program is kind of chugging away. A programmer, either through lazy coding or other practices, creates a buffer in code but doesn't put restrictions on it, basically saying, if the buffer is running dry, maybe send some kind of message that the system's going to run idle. Or if the buffer is getting overloaded, you need to be able to truncate that data and say, okay, we're not going to accept any more inputs until the buffer has been, whittled down by a certain percentage. Like too much water poured into an ice cube tray, the data has to go somewhere. So this traditionally means that there's some kind of adjacent space in memory to where this data gets written. This can lead to overwriting, this can lead to corruption, this can lead to system integrity loss, or the disclosure of information to third parties that are unauthorized. Using targeted buffer overflows and similar structures, we can actually force the system to output data into a clear text or a more visible aspect of the system to where it can be captured via terminal or similar, so that you could find potentially sensitive information like logons or cryptographic keys or things like that. So there's all kinds of forcing that buffer overflow can occur. One of my favorite examples, I believe, was from the game Dark Age of Camelot. And there was a player who figured out that you could actually buffer overflow the inventory for a particular item so that it went into using a negative number, essentially, so that when you tried to sell a negative number of the item, it would try and subtract more than was there, but there was no protection in place to say that you couldn't do that. So it ran the buffer overflow the other side to where it gave him we'll say 2 trillion of a particular item, completely wrecking the server economy for that particular location. And it was a simple, it could have happened on accident very easily. It wasn't like it was an intricate number of steps that had to be put into place. Denial of service. This is something you'll hear about all the time. Somebody getting DOS hammered. So denial of service is where some resource of the web server, sometimes multiple resources, are being rapidly consumed, and the bandwidth is getting eaten up, and you can't control legitimate connection. The system isn't able to respond normally, so this is mostly considered to be an annoyance, but can be very severe depending on what's going on. You also have what's called a distributed denial of service, or DDoS. It's the same goal, the difference is scale, and it also can sometimes circumvent some of the protections that we expect to see for a DOS attack. So a DOS attack is if we do a ping flood, which we'll talk about in a little bit of time, you'll see there it's the top of the right column. That can be fairly easily circumvented if it's only coming from one host, because it's like, hey, this one person is putting in too many requests. We're going to go ahead and shut them down. We're going to keep them from transmitting for a certain period of time. With DDoS, if we have 10, 100, 1,000, 10,000 people all under the control of a bot network or similar, and they are producing these ping flood requests or whatever we have, SYN floods, could be any number of different variations, then how do we sift out legit traffic from potentially hazardous traffic, malicious traffic? So we have a larger number of systems by far that are trying to smack the target with a particular amount of data to cause it to go under. And it's much easier to do with DDoS than DOS. It's a lot more coordination, but the hit is much more productive for the attacker. So let's look at some of these examples here. Ping flooding. This is where a computer sends a ping to the system with the intention of uncovering information about it. Now, generally, this is not considered malicious in and of itself, but if we scale this up so that the packets become larger or incredibly frequent, things like that, we can cause the system to go offline or suffer slowdowns as the resources get tied up. Smurfing attack is similar, but with a twist. In a Smurf attack, we send a ping command to an intermediate network where it becomes amplified and is then forwarded to the victim. Then this ping becomes a virtual tsunami of traffic, usually DNS, things like that, to where you can spoof somebody as being a DNS respondent. So a DNS server obviously would be built to handle a significant number of multiple connections simultaneously. Individual users traditionally are not. So now we're, engulfing this individual. SYN flood, the equivalent of sending a letter that requires a return receipt, but the return address is bogus. The return receipt is required, and we have no return address or no legitimate one. The receipt goes nowhere. And for a period of time, the system just kind of sits there and waits, timeout, things like that. If we send enough SYN requests within a period of time, we can actually lock the system so that all the connections are currently half open and nothing else can get through. IP frag or standard frag attack. This requires slightly more advanced knowledge of the TCP/IP suite, so we can break up packets into fragments that can bypass most IDSs. IDSs will be like, hey, you can use stateful inspection or what have you to try and determine what the content is. And if we figure out it's something that's malicious, or if it's dummy data, or if it's trying to carry out one of these frag attacks, there are signatures, behavioral signatures, usually called heuristics. But if we fragment this, it can't necessarily apply the intelligence necessary to say, this piece belongs to this piece, let me temporarily assemble it, inspect it, and then let it go on. The overhead time and computationally would be too much. So fragments get passed, they get reassembled on the other side, and then whatever the attempt was is able to go through. So you have a SYN flood that can bypass a firewall, or a ping that can bypass a firewall. This can cause blue screens, reboots, freezes, system locks, server hangs and reboots. So there's a lot of stuff that can go on with fragmentation. Banner information. Banner information originally was designed to just be able to give you an idea of whether or not you were connected to the correct location. So unfortunately, with people trying to be helpful, I guess, you run into a situation where the banner starts revealing information about the server that we did not intend. It may show versions of what's running, what type of server you have, it's Apache, X, Y, or Z version, or you have, Microsoft IIS running version, 6.0 or 7.0. And as we know from our discussions about vulnerabilities, if we know what version of something is running, we can tailor our attack. We can find vulnerabilities specific to that particular version. So if we run, telnet www. Whatever the server is, port 80, we may get results that look like the graphic here. So we've got http/1.1 200 OK. So it's returning a 200 code. And then we've got our server name and version. And then we've got our content location. So we're defaulting to an index.htm. Okay, got some information about that. If it were something like an ASPX or on any number of different extensions, that might tell us some information, obviously. And then we've got some tags, we've got some content length. If we know the content length, possibly we can try and spoof some buffer overflow to try and force it to read data beyond that content point. So there's a lot of different things that exist in a banner grab that might tell us very detailed information about the system if we know what to look for. We also have to be concerned about permissions on a web server. Permissions control who has access to what. Who has access to a control dashboard, who has access to content, who has access to be able to turn various things on and off. Permissions about permissions can exist. They can also be incorrectly configured. So if we have incorrectly assigned permissions, we can allow access to locations that shouldn't be accessible. Older web servers used to allow directory traversal by default. So you used to be able to just navigate up or down throughout the structure. You couldn't necessarily access certain files, but you could see the overall structure of the system and possibly be able to try and brute force your way. If you were entering in a path, using the double dots in order to give a relative pathing indicator, it may be able to allow you to jump from one directory to the next and be able to access files there by using some kind of implied permissions. We have to remember from any programming we may have discussed the concept of inheritance, the idea that a child process will inherit the permissions of its parents while it's running. So if somebody writes in a macro and something is running through Microsoft Word, if you open Microsoft Word as an administrator and then open that Word document, it's going to inherit administrator permissions. It could possibly be running scripts that could be deleterious to the system. Some error messages we might see, usually going to start with a 4 with HTTP. We can see a number of different items that could be potential vulnerabilities. So we want to be aware of what is it that we're actually showing. So this is for several IIS messages. Why something failed. Is it authorization? Is it forbidden? And what we can do is, if we can feed specifically crafted information to the web server and we get certain error messages back, we know how it interprets certain types of messages. When we do that, we can guess how it might respond to a particular malware payload. Servers should be purpose-built. This is something I saw quite a bit when I was teaching CTS 120 in the earlier parts of my teaching career. And I would see, I have students write a term paper, essentially, that says, build me a custom computer. I want it to do, pick a category. I want it to be custom built for a purpose. And people have this mental block about wanting computers to be able to do everything. They want it to be a Swiss Army knife. But the problem is, when you include all these features, you also have to include a lot of foresight about how these features might be subverted, or is this going to be necessary? Is this going to be wasted space or wasted functionality? And it takes a little bit of educational deprogramming to get that to kind of fade out. So servers should be purpose built. They have to fill a role. If you have a server for your email, if you have a server for your web products, if you have a server for your database, those should not all be on the same machine. They can be, like technically, but they should not be. That's a bad choice. You always want to put as many layers as possible between the outside world and a single device. If you give somebody access to a web portal to get into the web server, that is a measure of trust that's being imparted. So if they breach that, do we want that to infect everything that's in the system? No, we want to isolate that. So again, just separating systems, even if they're running in containers, can be helpful. Anything not essential to the role for which the server was built should be eliminated. And then we should perform general hardening. So this is where we go in and we change default passwords and we remove any feature, service, or application that is not necessary. Now, in some cases, they'll say, let's just go ahead and disable the service, turn it off. If we can, we should go in and uninstall it. And the reason for this is, if we have a situation where a particular feature or service is just turned off, how simple is it to just turn it back on again? Especially if it's a service that traditionally runs by default. If we can run some sort of script that forces it to resume its original default operation, then boom, we're able to get back the initial active position instead of inactive. So it's important to make sure that you have those things in place. User accounts, of course, we want to be able to be scalable. We want to be able to have access for a number of different users and a number of different user types. Now, most operating systems will come pre-configured with user accounts, groups, and roles and things like that. These definitions are already in place, but they may not necessarily be explicitly defined. They may not tell you what they do and don't allow unless you go digging. Now, these accounts can easily be discovered through research by an attacker. Once we figure out what defaults might be present or what things we can guess, then we can try and gain access. So in general, what I would do is say, if you have a server that you're going to use, make sure that you set up a standard account, not the default. Don't customize the default. Remove the default, create a new one, and make sure that you have a separate administrative account. So create your admin account, create your standard user account, and then delete the defaults. That's a strong recommendation for me. The reason I say to do this is because if there are predefined permissions that are already there and you don't know about them, you are automatically incorporating those. Again, tying back to the inheritance thing we were talking about a moment ago. SQL. SQL has many flavors and implementations and a ton of uses. But SQL is also susceptible to injections because web applications are built from this structured query language. They're built to accept these particular requests and then process them according to the rules. Now, if we can craft a query that can circumvent these rules, then we can get information back that was not intended. The attacker injects the code into an input box, publicly facing, a form, or directly into a network packet. You don't even often have to have a portal form. Then these commands can then exploit non-validated input vulnerabilities. It can be used to arbitrarily execute commons in the SQL language through web applications. So if you have something that is, a print command, and you just change what it's printing, instead of having something that's from a protected source, you can try and push back towards a more raw or exposed aspect of that particular database entry. So let's take a look at an injection. If a website lacks input validation, meaning that it doesn't check to see what's being inputted before it processes it, only a web browser and SQL knowledge are needed to be able to carry out an attack. SQL injection is incredibly common, and it's very, very serious with websites that employ a back-end database, something that allows you to retrieve certain amounts of information. So we put special characters into existing SQL commands and modify the behavior to achieve the desired result. You can also do, a lot of times when we deal with SQL injections, there's a lot of probing. So we have to be aware of if we see certain strings coming in from inputs, we may want to be aware of what's going on. And of course, data sanitization or input validation is going to be the big part. So let's say we have an attacker, Kirk, just general. We have a string that Kirk inputs that says name, semicolon, delete from item, semicolon, dash, dash, for item name. So the query actually becomes two queries because of the structure here. So this is where we have select all, that's what the asterisk is, from items where owner equals Kirk and item name equals name. Delete from items. If Kirk enters the string name delete from items, select all from items where A equals A, the following valid statements are created. And statements are going to be separated by semicolon. That's going to be considered a standard statement. Select from items where owner equals Kirk and item name equals name. Delete from items. Select all from items where A equals A. Now the last part of that is really what we're looking for. Where A is equal to A, we are doing a character-to-character implicit test. Something equals itself. Now, if we conjoin all of these items together and that piece is true, that will allow us to circumvent the other two pieces and automatically accept them. So by including these 1 equals 1 or A equals A statements, we can sometimes bypass the selection process by automatically getting it to give us the information by using a known tautology or always true statement. Now let's take a look at XSS, or cross-site scripting. This is just a generic attack, so we're going to take a look at the structure and see what we're looking with here. An attacker discovers a defect on highroll.com and sends a fake prize email, cross-site script. Link in the email to collect the prize goes to the address given here, highroll.com/default.asp, question mark, name equals, it's the tag, script, evil script, method call, close script. Okay, so on click, the website is going to display welcome back with a prompt to enter a name. This name is going to come from your browser via the email, which tells the site your name is the script. The server reports the name and returns it to the browser, which correctly interprets it as a script and runs it. So it's going to look for this bad script and goes ahead and says, okay, now the browser is going to be instructed from the script to send a cookie containing information to the attacker system. So this could be login information, this could be any number of things that you would input as part of accessing the site. And the site behaves normal. So once you've gotten that information in, this cookie is just sitting there kind of quietly taking notes on what you're doing and then sending it on. So it's kind of difficult to detect cross-site scripting unless we are aware that a script is being passed in instead of the expected entry data or things like that. And then, of course, those attacks can be tailored to hide themselves even more discreetly. We have to remember that all of these commands, in this incredibly simplified example, are legal. So you have to remember the difference between syntax and semantics, definition and meaning. Syntax is structure. Syntax is just how things are written. Semantics are, what does that mean? What does it generate? What is the intention? It ties back to something we hear from the time we're children. There are no such thing as bad words, just bad intentions. And technically that's true, but bad words can be used to convey bad intentions. In this case, Bad email links can be used to convey bad scripts. The browser isn't doing anything outside of following its instructions. And the instructions given were crafted to circumvent some of the security features we expect to see on a website of this type. There are some implicit assumptions that are made. So the system is like, yeah, we'll just progress as normal. We're just going to incorporate this script because there's nothing saying that we shouldn't. So in web applications, we have some exploitative behaviors to be concerned with, of course, information theft and destruction, credit cards, other types of sensitive data, and passwords, of course. The ability to update the application and site content, buffer overflows, server-side scripting exploits, DNS attacks. We also have some different vulnerabilities that form categories of things that can be targeted when people are trying to break a web app. Usually AAA, so authorization, authentication, and accounting. Configuration problems, input validation, session management, encryption, and then environmentally specific problems, which are very, again, very specific, proximity to a certain physical object or whatever else. Now, if we have a logon system that provides error messages, we want to make sure that we do not provide identifying information or normally the kind of information that we wouldn't want to share. So an example of a revealing error message is shown here. This user is not active. So do we assume that this means that the user does not exist in the database, or the user does exist in the database and we just put in the wrong password? Have they been made dormant by an administrator? Things like that. Information relating to improper or incorrect user logins could be invalid user ID with a valid password, a valid ID with an invalid password, or an invalid user ID and password. All of those things should provide different error messages by default. We want to change it so that it doesn't share anything that's potentially identified. Scripting errors can occur, of course. Upload bombing. This is where upload bombing throws masses of files onto a server trying to fill up the hard drive so that it can crash the application that the server is hosting. Poison null byte passes special characters that scripts may not be designed to handle. This is where a script may be able to grant access where it otherwise would not be given. Default scripts are uploaded to servers by designers who do not know what they do at a fundamental level. In such cases, an attacker can exploit configuration issues with those scripts and gain unauthorized access. This is where people are building websites by using, Stack Overflow or things like that without knowing what the script does. So they just copy and paste, the page runs, and then there are these little pieces of code that are floating in the background that are going to be potentially vulnerable. Sample scripts, sample content. If these things aren't commented out or outright deleted, they can lead to potential vulnerabilities. Poorly written scripts, questionable scripts, all of these things can leave some definite exposures in terms of passing things in plain text or being able to duplicate credentials to a secondary location. All of those are going to be considered poorly written. So let's take a look at sessions a little bit, specifically session management. Sessions just represents the connection between the client and the server. Two hosts are communicating with each other over a network medium. That's a session. Now, session information can give an attacker access to confidential information. The session will contain a unique identifier, what encryptions are present, and several other parameters. So let's look at some of these different bullet items here. Long-lived sessions. We need to make sure that the management process terminates any session that is not needed any further. So we initiate the session, we communicate whatever information we need, we terminate. Sessions that remain valid for longer than needed allow attackers using cross-site scripting or similar to retrieve the session identifier and be able to reuse it. Logout features should be present so that visitors can log out and close the session without having to close the browser. In certain cases, closing the browser doesn't actually terminate the session properly. Insecure or weak session IDs. In certain cases, the way that they're generated, if there's not a pseudo-random algorithm or things like that, they can be pretty easily predicted or guessed. If that's the case, then that can be a very negative possible vulnerability. again, it ties back into the being able to reuse session IDs. It's even worse if you can generate seemingly legitimate ones based on a known algorithm. Session IDs to unauthorized users. This is where they can be redirected to a logout page. If a session ID has been granted at that point, it could possibly be repurposed to request a valid URL instead. Absent or inadequate password change controls. If we want to change the password and it doesn't require us to put in the original password at the same time, that can be problematic. Now, obviously, if we've forgotten a password, we have to process that a little bit differently, but that'll use usually some form of multi-factor in order to validate the user in question. Inclusion of unprotected information in cookies. That ties back to what we were talking about with the cross-site script earlier. The Hyrule site had a vulnerability where cookies could be generated and capture login or session information to be passed over. It can also give us an idea of what the web application is actually doing and how it's built. Some weaknesses to encryption: weak ciphers. If the cipher just doesn't have the strength necessary to be able to carry out what is needed, then we're going to have a problem with the site being able to be broken through rainbow tabling, brute force, etc. So the attacker can then easily decrypt the data, gain access. Vulnerable software. Certain software implementations like SSL may have poor programming, so TLS might be a better choice. Older encryption methods are often susceptible to brute forcing. So, if you have a cipher that has been faded out, if you're using SHA, you should try and stick to 2 and 3 as opposed to going back to the original, because as computer power increases over time, the ability to brute force it or an analysis of the algorithm that could lead to more procedural breakage could be possible. Databases themselves could have issues. Information about the site, the application, these are considered a holy grail because once we can crack the database, we can dump a massive amount of information. Configuration data, application data, user data, cryptographic information, tons and tons of stuff. Now, databases traditionally come in two flavors: relational and non-relational. Relational database is where data can be organized and accessed to fit a scenario and is stored as a collection of tables. So query languages like SQL will be involved in order to retrieve that information from the table. So that's where we get the select from. So we're going to say from this particular table or number of tables, we're going to select information that matches this criteria. So that's why SQL is so powerful, but can also be very easily manipulated. Non-relational or NoSQL-based databases are a couple of different sub-varieties. Key value store is a very popular one. Data stores in this format, like Hadoop or Cassandra, grew from a need to store and retrieve large volumes of data in a short period of time. Being able to retrieve information from tables and filter it through the query system is computationally more intensive. So we might see things like misconfiguration. Of course, we talked about that. Lack of training. If somebody doesn't know how to use the system and inputs data in a way that can be more predictable or possibly extracted through other types of exfiltration. Buffer overflows, as we've talked about. What is the buffer size for a particular iteration of the software? How big is the table? What is the what's the content of a particular column? If it's a varchar size 20 and we push in something that's over that size, what's going to happen? What is it going to retrieve in terms of information from the next column over? Forgotten options. Like I said, if we have a piece of software that has options that we don't know about, how can we protect against that which we don't know? And there's all kinds of other oversights that might be included as well. If we're trying to locate a database on the network, we could use things like Network Database Scanner, SQL Recon, OScanner. These are all very different implementations. So if we're using Microsoft SQL, that SQL Recon would obviously be a good idea. OScanner is for things like Oracle. The graphic we see here on the right is for SQL Ping 2. So this is a scanner. We can also use if you could see in the top bar there, it says utility in between settings and help. I believe there's also a password cracker included in Ping 2. There is definitely one included in SQL Ping 3. See here, I've got it listed with my cracking tools. Cain and Abel, also a very common password crack tool set. And then there's also some dictionary-based cracking methods we can use as well. We can have, some salting, some rainbow table generation, things like that. So those will work as well. There's a ton of different cracks out there, but you want to specify based on what type of database you're experiencing. A lot of different tools that you can incorporate to try and figure out what kind of database you're dealing with. To be able to locate vulnerabilities in a database, again, you can run scans, you can do probe queries, you can, go through the CVSS or CVE guides. Stored procedures are pretty common. Service account privilege issues, poor authentication methods, and then limited or no audit logs. That one is really concerning. If you have a relational database, the logs should constantly be churning out information simply because of, depending on your size, really, there should be some kind of access log that identifies any queries coming in, any kind of maintenance, any kind of updates, any kind of copies. Security through obscurity is a bad idea because of this principle here. Out of sight, out of mind. If we have something that is not immediate and visible, it is sometimes easy for us to assume that no news is good news and everything's working. So if we have the out of sight, out of mind principle, it means if we don't pay attention to a particular vulnerability, then we're not going to think about it as time goes on. It will become less and less of a priority and much more likely to be exploited. So learn your security features, know your database system, test things out. Evaluate the use of non-standard ports. What ports need to be active, and that's where the logging comes into play. What ports are actually committing traffic, and does that match up with the services we expect to see? Keep up to date. Keep things patched. Make sure that if there's an issue that you're seeing, again, that comes into logging and auditing, that we are addressing that. On occasion, you may actually need to create a secondary table and migrate the information so that way you can make sure that somebody's not trying to brute force the primary keys for a particular entry in your tables. Secure the operating system. The operating system that hosts the database structure needs to be just as secure as the application itself. And then, of course, firewalls. We kind of tie that to the non-standard ports thing as well, because we need to make sure that data filtration is correctly being applied. Last but certainly not least for this discussion, we have to remember that cloud computing is also part of the database system. We're accessing a database remotely. It's being hosted by somebody else. It can be a platform. It can be infrastructure. It can be software. Usually we just say XaaS, which is anything as a service. Whenever we're dealing with cloud computing, of course, we can go much, much deeper. There are three main issues that I like to talk about: availability, reliability, and loss of control. Because remember, this is being hosted by somebody else. So the ability to go in and troubleshoot is dependent on another agency. Because the environment is offsite and accessed via the internet, availability is a huge concern. Any internet outages in between your client and that hosted resource would affect availability of services dramatically. Cloud service providers tend to invest pretty heavily to ensure minimum uptime guarantees, but you're still at the whim of a vendor. So reliability is not in your hands. So you have to have some backups on occasion. And then, of course, loss of control. If we have stability issues or if things are moved from one site to the next, if there's migration or updates, it's not necessarily something that's controllable by you as the client. It has to be something that's communicated as part of your service level agreement or SLA when you set up your contract with the computing provider. So we covered a lot of ground today. We talked about server and application vulnerabilities, tools, and exploits. We talked about database attacks and tools. This, of course, is a very surface level exploration, and there are tons of things that we will talk about going forward. If you have any questions or concerns about the materials we've discussed and want to push that further, certainly message me through Teams or through the YouTube channel here, or through Blackboard or through my WakeTech email. Just let me know if there's anything I can do to kind of help increase your understanding. This is a very, very deep topic, and this is something that you'll spend a ton of time on if you're preparing to take the CEH directly. So please just contact me through the usual channels or come by the office, always glad to see students come by. I'd love to meet you guys. Hope you're having a wonderful rest of your day, and thank you so much for your time and attention, and I will see you next time.